Right, number 7 on the practice final exam gives us h of x and p of x, and we're asked to write the simplified form for h composed with p of x, which means we're going to take p of x, which is 5 minus x, and we're going to substitute it right in here for x. So this is going to be 4 minus 2 times 5 minus x squared. Now, order of operations says I have to do the exponent first. So off to the side, I'm going to do 5 minus x times 5 minus x, which gives me, I'm going to FOIL this, 25 minus 5x minus 5x plus x squared in simplified form, and we usually do things in descending order. It would be x squared minus 10x plus 25. So this is going to be 4 minus 2 times x squared minus 10x plus 25. Now when I go to distribute, I have to remember to distribute the negative 2, not just 2, but negative 2. So I get 4 minus 2x squared plus 20x minus 50. And the 4 and the negative 50 are my like terms. So my final answer is negative 2x squared plus 20x minus 46. Now, number 8 in its learning has us, gives us the same h of x and p of x, but then it asks us to do p composed with h of x. So I'm taking h of x and putting it in to here. So I get 5 minus 4 minus 2x squared. Distribute this minus sign to both, and I get 5 minus 4 plus 2x squared. So my final answer would be 2x squared plus 1, because I like to do it in descending order. So that's 7 and 8. All right, 9 and 10 have to do with writing a translation rule. We're told that y equals 2 divided by x. This is my parent function, my original. And then this is my translated function. And I have to look at how it's changed. In the equation, I went from x to x plus 5, but remember x lies in the equation. So in the translation rule, that would be x minus 5, but y tells the truth. So I went from having nothing here to having minus 6, so that'd be y minus 6. That would be my translation rule for number 9. And so for number 10, again, this is the parent function, and this is the translated function. Notice that in the equation, I went from x to x minus 5. So in the rule, that's going to be x plus 5, since x lies in the equation. And I have y minus 6, because y tells the truth. So that's my translation rule for number 10. All right, number 11 gives me the ordered pair to negative 7. And we're asked if this was an even function, name another point on g of x. Well, if it's even, that means it reflects over y-axis. And so if I was to move to negative 7, 2 negative 7s over here, and I reflect it over to the y-axis, it would move over to here. So the y doesn't change, only the x-coordinate changes. So the 2 becomes a negative 2, but the negative 7 stays the same. if it was odd, it rotates 180 degrees about the origin. So when it rotates over to here, what happens is both x and y change. So it becomes negative 2, because we're always looking at the original. The 2 becomes negative 2, and the negative 7 becomes positive 7. Because if we went 180 degrees and we landed over here, my x-coordinate would be negative and my y-coordinate would be positive. Inverse means that you switch x and y. So the negative 7 becomes the x, and the 2 becomes the y. Number 12, we're going to do a similar type problem. So for number 12, we have negative 2, negative 7, which would be over here in this quadrant. Even, again, I reflect over the y-axis, so my x-coordinate changes, but my y stays the same. So it becomes positive 2, negative 7, because it would move over to here. If it's odd, it goes 180 degrees around the origin, and so I'm going to move from here to here. Both x and y change, so it becomes positive 2, positive 7. And for the inverse, I switch x and y, so I get negative 7, negative 2. Okay. In number 13, we're told that the sine of theta is 4 square root of 11 over 15. And we're also told that theta is in quadrant 1. So remember that everything over here in quadrant 1 is positive. Sine is positive, cosine is positive, and tangent is positive. All three of them are positive, which makes it kind of nice. We don't need to worry about positive and negative signs. We're asked to find the exact value of the cosine of theta. Well, we had the Pythagorean identity theorem that told us that cosine of theta squared plus sine of theta squared equals 1. So cosine is the part that I don't know, plus I do know the sine squared equals 1. So cosine squared of theta plus, when you square 4, you get 16. When you square the square root of 11, you get 11. And when you square 15, you get 225 equals 1. Right, I'm going to keep going here. Cosine squared of theta plus, when I do 16 times 11, I get 176 over 225 equals, I'm going to call this 225 over 225. Since I'm solving for theta, I'm going to subtract the 176 over 225. That's why I changed this to 225 over 225. And I'm just going to come right up here. And I get that the cosine squared of theta equals 225 minus 176. So 225 minus 176, I get 49. Now I have to take the square root. I would normally need plus or minus, but since I'm in quadrant 1, I only need positive. And the square root of 49 is 7, and the square root of 225 is 15. So my exact answer is 7 divided by 15. So 14 is a lot like 13, where I'm given the sign. I'm told that it's in the first quadrant. So again, everything in quadrant 1 is positive, and I'm asked to find the cosine. So I'm going to use my Pythagorean identity theorem. And I'll put this sign in right here. So I get cosine of theta squared plus 2 square root of 30 over 13 squared equals 1. So I get cosine squared plus, when I square the 2, I get 4. When I square the square root of 30, I get 30. When I square 13, I get 169 equals 1. So I get cosine squared of theta plus 120 over 169 equals, I'm going to call this 169 over 169 in anticipation of needing to subtract this. Then I subtract 120 over 169. And I get cosine squared equals, I got 49 over 169. When I take the square root, I don't need to worry about plus or minus since I'm in quadrant 1 and I know everything is just plus or positive. I get 7 over 13. In number 15, I'm told that the tangent of 115 is approximately negative 2.14. So I know that 115 is over here in quadrant 2. It will be somewhere over here. And this is where my 115 degrees would be. And when I look at that, I'm like, okay, I know that the tangent is negative in quadrant 2 and in quadrant 4. So since it's in quadrant 4, I know that when I go straight across, that's 180 degrees. So I could simply take 115 and add 180. And I get 295 degrees. So this angle here, 295, would have the same tangent as 115. Because, again, tangent is positive in first and third and negative in the second and fourth. So when you're just going across the diagonal, the easiest thing to do is add 180. If we were going the other direction, we would have subtracted 180. I don't need to find the reference angle because I don't need to find the quadrant 1 or 3 answer. If I was looking for the quadrant 1 or 3 angle, I would have to first find this reference angle. But because I'm going diagonally, I just need to add 180. If you're wondering, well, how would I find the reference angle? Well, think about it. Right here is 180. So this reference angle is 180 minus 115, which would be a 65-degree angle, which makes this 65, this 65, and this 65. So this will be 65 degrees. And right here would be 180 plus 65, which would be 245. But the one that has the same tangent as 115 is this one right here. Okay. Number 16 is similar to 15. They tell us that the tangent of 57, which would be right here in quadrant 1, is 1.54. Find the tangent find another angle that has the same tangent. Well, again, tangent is the same on the diagonals. So the other angle that's going to have the same tangent is diagonal, so we just take 57 and we add 180, and I get 237 degrees. This is my final answer. I could find these other two angles by realizing that this is 57, the reference angle, and to find this one, it's 180 minus 57, and this would be 360 minus 57 if I wanted to find these two.